On to our next topic. This doesn't look like a new topic, does it? Students will be able to solve linear systems and interpret their solutions. Well, you've been doing that since Algebra 1. So, we want to think about doing 3x3 systems, which we just were doing with matrices, right? And we want to kind of think of them graphically now. We're actually finding the intersection of 3 planes, right? So there's 5 examples of 3 planes, some that meet, some that meet, some that don't. This language you had in AAF, and I told you that IB likes this language when describing solutions of systems. Remember, when you had a 2x2 system, 2x2 systems either met in a point, and we called that independent, consistent. They did not meet at all. We called that inconsistent. Or they were coinciding lines, so they had infinite solutions, and we called that a dependent consistent system. We're going to use that same language here, and even though I told you it was IB that liked this, they like it because there's a piece of linear algebra on the HL exams. This is really linear algebra vocabulary. So, any system with no solutions is called inconsistent. So look at my 5 choices up there. I think it's pretty obvious one of those pictures is inconsistent. But did you know that there's 3 of them? Right? An intersection of 3 planes is what I'm looking for. 3 planes, right? There is an intersection, but not of 3. There is an intersection, but not of all 3 at once. So all 3 of these are inconsistent. A system with 1 or more solutions is called consistent. So if you're not, these are mutually exclusive. If you're not inconsistent, you are consistent. Right? Both of these are consistent. But I can break down consistent systems into 2 subcategories. If the solution is a point of these 3 planes, there is one unique independent solution. So we call this consistent independent. If there is more than one solution, we call this consistent dependent, because it depends upon having more than one solution. Okay? So we have found ways to do this, right? We have taught you already some methods to solve a 3x3 system, but now we're just asking you to think of it as finding the intersection of 3 planes. So there you go. There's a 3x3 system. And instead of just looking at it as algebraically, I want you to think of them as 3 planes, right? And remember from the equation of planes, there's the normal, 4, negative 5, 3, 1, negative 1, negative 2, 4, negative 4, and negative 14. Right? That's the normal vector. That's the power of seeing the equation of a plane, is you have the normal right there in it. So we have taught you to solve a 3x3 system by the elimination method in AAF, which is just building on the elimination, right, the add-down method that you learned in Algebra 1. Then in AAF, we also taught you to solve inverse matrices with, solve a 3x3 system with inverse matrices, and we redid that this year. And then this year we added another method of solving a 3x3 system called Cramer's rule. Now we're going to add a 4th method. And this 4th method really is the elimination method. It's just a very algorithmic and organized way of using the elimination method, and a very systematic way to keep track of what you've been doing. And this was made famous by a very famous mathematician called Friedrich Gauss. And sometimes this is called the Gaussian elimination method. They call it the reduced row echelon form. Echelon refers to like something that looks like, that is step-like. Okay, form means there's a required form in order to meet the requirements of being reduced row. And reduced row means you've used something called row operations to get into that form. Row operations are really no different than what you've done in Algebra 1 and what we did at the beginning of AAF when I said, here, you can take two functions, you can add them, subtract them, multiply them, right? And then using the elimination method, you can multiply one function by a constant and add it to another function. You can switch orders. Oh, she said later.
Okay.
So these are all, this is what reduced row echelon form, which sounds kind of annoying to say and to keep saying. So sometimes sometimes we use RREF, reduced row echelon form. I haven't even told you what that form looks like yet. But first, before I do that, I want to tell you that step 1 to row reduced echelon form is to create an augmented matrix. Augment means add to. So this is a 3x3 system, and we know that a lot of our matrix algebra works when we have a square matrix. But look at this matrix. This is not a 3x3 matrix, is it? It's a 3x4. But we call this a 3x3 augmented matrix because it's been augmented with the answers, the answer column. So we are still going to consider that this is a 3x3 system, and we are just adding one column or augmenting the matrix to include the answer column. So that's step 1. Step 2 is to use row operations to get to the identity matrix for a 3x3. For the 3x3 part, not the augmented part. So you're trying to get this matrix to look like the identity matrix, which means you need ones in these positions and zeros everywhere else. Okay? So that's our goal. Why we like that goal, I'll show you in a little bit when we're done. So, to solve a system of planes by the RREF method. Now the next I'm going to hit a button and you're going to go, ah! So here I hit a button, now go, ah, everybody at once, right? Don't copy this down. You can take a picture of it, you can refer to it later because you've got the video, but I don't want you to spend time writing this down. I just want you to watch what this notation means, and then, right, as I talk through it, and then we will do an example together. But I want you to look and see that you have started with our augmented matrix right here. And look at the 3x3 part. And when I'm all done, look at the 3x3 part. Okay. So let me tell you what this language means. Row operations, each one of these things is a description of what operation I performed on rows. So the first thing I did was just switch the position of row 1 and row 2. I still have the same matrix, right? I just took row 1 and row 2 and switched them. And can you see why that was advantageous to do? We call this a pivot, right? I have a pivot spot there of a 1. Now, don't look at this right now, just look at the next matrix. Can you see that from this matrix to this matrix, I just copied row 1 over, and I copied row 3 over. Whatever I did, I replaced row 2. So it's as if whatever I did turned into row 2. So here's the operation that I've done. I took my old R2 and subtracted 4 times R1. So let me go to here to above my R1 and multiply everybody by 4. 1 times 4 is 4. Negative 1 times 4 is negative 4. Negative 2 times 4 is negative 8. And negative 6 times 4 is negative 24. Now, take row 2 and subtract that. 4 minus 4 is 0. You see why that is something I like, given what you know, what I told you that reduced row echelon form looks like and where I'm trying to go. Then I did negative 5 minus negative 4, which is the negative 1. 3 minus negative 8, which is 11. And 2 minus negative 24, which is 26. Okay, so I have a pivot here, and I have a 0 underneath. Now, the next thing I'm going to say to do is I'm going to manipulate row 3 minus that same 4 of R1. Notice again that I copied over row 1. I copied now over what I had done to row 2, and I'm going to change row 3. So this operation I did and then replaced row 3. So I still have 4 times R1 up here. So what happens when I take row 3 and subtract that? 4 minus 4 is 0. I like it. Negative 4 minus negative 4 is also 0. I like it. Negative 14 minus negative 8 is negative 6. And 18 minus negative 24 is 42. So this one was the change. Next, I just took R2 and multiplied it by negative 1, or changed the sign of everybody and replaced row 2 with that. And you see why that's advantageous, right? I just changed the sign. Changing the sign of 0 doesn't do anything, but changing the sign of negative 1 gets me another pivot position. And now look at what I have. I'm so close. Right? I'm really getting there. So I just changed the sign and replaced row 2. Now look at the next thing that I'm going to do. The next thing I'm going to do is simply add row 1 and row 2 over again. And can you tell where I'm going to replace that? Look at the previous matrix. I just copied row 3 and row 2 over, but row 1 is different. So I took row 1, added row 2, and replaced row 1 with it. So 1 plus 0 is 1, but negative 1 plus 1 is a 0. Here's another 0 I got. Negative 2 and negative 11 is negative 13. Negative 6 and negative 26 is negative 26. But look what I got. I got another 0. I got 1, 0, 0 and 0, 1, 0. Next, I'm going to just take row 3 and divide it by negative 6 or multiply by negative 1/6. Then I'm going to replace row 3 with that. Oh snap, I got my last pivot. Now, row operations don't have to be done in my order. As long as you get where you want to go and you're doing everything legal, it doesn't matter what order you do these things in. Now I'm going to put a little star next to this, because I want you to notice that I have succeeded in getting my pivot points, my pivot ones, and behind all of my pivots are zeros. If I can't go any further than this and get all the way to reduced row form, this matrix is good enough, and I'll show you why when we get done. That's why I put a little star next to it. Is often good enough, I should say. But let's go on. So hopefully you can see that what I've done is copy this over, and I changed again row 1. I took row 1 and added 13 of row 3 to it and replaced R1. And hopefully you can see why I did that, right? If I multiply this times 13 and add the negative 13, that's how I got this next 0. Right, so now I took care of that column and took care of that column. I'm kind of trying to work on this column now. And then hopefully you can see why this was next. R2, I took row 2 and added 11 times R3 to get rid of that negative 11. And now I'm in full out reduced row echelon form where I have the 3 by 3 identity here. And remember, we augmented this matrix, right? We augmented this matrix, and the first column represented the x coefficients, the y coefficients, the z coefficients, and these represented the answers. And I've just been doing Algebra 1, truly. And look at what this now says. Let's read bottom up. 0 times x plus 0 times y plus 1 times z is equal to negative 7. What does this row say? 0 times x plus 1 times y plus 0 times z is equal to negative 103. 1 times x plus 0 times y plus 0 times z is equal to negative 123, which means these three planes intersect at a unique point, and therefore this system is consistent because I got an answer, and it is independent because that answer was a unique point. Wow, a lot of work, huh? Now I want to go refer back to this star. Can you tell why this one was actually good enough? If you look at this last line, I still get z equals negative 7 out of it. But because I have these zeros behind here and here actually, can you see that this just says 1y minus 11z is equal to negative 26, and this says 1x minus 13 times z is equal to negative 32, and trust me, you'll get negative 123 and negative 103 out of that. Okay? Whoa, that was a lot of work. And it is a very hard skill to learn which one of those operations you should do when, and it's only certain systems for which this works out nicely by hand. So this is really all for computer programming, right? And which is, I find so fascinating that Gauss developed this system way before there were such things as computers. I find that absolutely ironic, or I don't know, just mind-blowing. I know, I'm a nerd. So, I forgot I typed that up. Here's what your homework is going to look like. Solve the system of equations and then name it. I didn't necessarily in the last one ask you to name it. If I don't ask you to name the system, you don't have to, but in this one I did. But you've just seen one. This is very abstract. It's not hard math, but it is hard to figure out which one of those operations to do, so don't worry. Whenever you have to do these by hand for us, we will give you the directions. Okay, so your homework will have any problem that I want you to do by hand. I will give you the steps. And if you can find a better or more efficient way than the steps that I gave you, please feel free. But let's go ahead and do this one. So if you want to pause and see if you can figure out what I did, please feel free. Remember, this really is a 3 by 3 matrix that I've augmented with the matrices. But I'm going to do my row operations on the augmented matrix. So the first thing I'm asking you to do is to take -2 times row 3, add row 2, and replace row 3. So I'm going to copy over row 1, copy over row 2, and then I'm going to multiply row 2 by -1, by -2. Right, I'm going to multiply row 2 by, multiply row 3 by -2. So that's going to be -4, -4, -2, and 16. And I'm going to add that to row 2 and replace row 3 with it. So 4 and -4 is 0. 5 and -4 is 1. 3 and -2 is 1. 17 and -16 is also a 1, right? Because I was multiplying by -2. I forgot that negative there. Check. Next, I'm going to replace row 1, so I'm going to copy over I'm going to do row 1 minus row 2. And that's going to get me 5 minus 4, which is 1. There's a pivot. And then one minus 1, 2, 5, 1 minus 5, -4, 3 minus 3, which is 0, 22 minus 17, which is 5. Whoops, I kind of knew that. I copied something wrong, huh? This is a 6, right? 5, 6. So this should be a 1. Sorry about that. Got sloppy with my writing. Six minus 5 is 1. Check. Now I'm going to replace row 2. So I'm going to copy over row 1, copy over row 3, and I'm going to do -4 times R1 plus R2 and replace row 2. So check my math on this. I'm not going to write it this time. Check. Negate R2 and add it to row 3 and replace row 3. Check. Divide row 3 by -2. Check. Next, I'm going to replace row 1. I stopped making my changes red. Sorry about that. Negate row 2 and add row 1. So I ended up here with 1, 0, -3, and 8. Then negate row 3 and add row 2 and replace row 1 again. And it is just convention. Yes, I could do multiple operations at once. It's just convention not to. Whoops, I lost my place, sorry. I did that. No, did I do that? Do that already? I should end up here, sorry. Oh, I think just this is a mistype. This is supposed to be row 2. Double check me on that. This is the row I replaced. Should be 0, 1, 0, and 3. And then when I do the last thing, 1, 0, 0, 2, 1, 0, and 3, and 0, 0, 1, negative 2. So again, I apologize right there. I kind of missed just a typo there. So notice where I am. I got myself to RREF here, which means that what I've got is z is equal to negative 2, y is equal to 3, and x is equal to 2, which means I have these three planes meet at 2, 3, negative 2. I got an answer, so this is a consistent system and a standalone unique point. All right, so there's got to be an easier way to do this, right? So get your calculator out for me, please. And enter the augmented matrix, right? Not the 3 by 3 matrix. Enter the augmented matrix in. So second matrix, edit matrix A. Your augmented matrix is a 3 by 4, right? So always double check and make sure that you've entered everything right. Right? 22, 17, 8, 3, 3, and 1, 6, 5, 2, 5, 4, 2. Yes! Now, go back to your matrix menu and arrow over to math. And arrow down, down, down. Look at that. RREF, what the freak? Are you kidding me? Hit enter. Oh crap. Whoops. Go to your home screen and hit second matrix math. Down, down, down. Any Johnny Cash fans out there? Down, down, down into the ring of fire. Hey, RREF could be the ring of fire. And I want the reduced row echelon form of which matrix? Bam, baby! Check that out. So, this is really nice. If you are asked for the reduced row echelon form and you have a calculator in your hands, you just need to know how to create the augmented matrix and then how to read the row reduced echelon form. That you have the identity matrix, so you actually have 2, 3, and -2 is the solution to your system. Holy cow. So you're on your homework. Now we still have more to do. Don't bail on me yet. On your homework, this is what your homework sheet looks like. Notice here, right? I say use the RREF, the Ring of Fire feature on your calculator, right? But I want you to write the reduced row echelon form down, except for 1 and 2. Hello, right? But then look at the back. On the back, I want you to do 7, 8, and 9 with the row operations, but I've given you what the row operations are. If you want to try to cover them up and do the, see if you can come up with the row operations on your own, or again, if you find a better, more efficient way and get to the same place as I do, please feel free. But we're not quite done because both of the systems that we have used have been, oops, I forgot to, oh no, I did, didn't I? Oh, I took away the annotations. I did name it, right? We got an answer to this system, 2, 3, -2. Therefore, it was a dependent, independent, consistent system. So let's do this one, but let's not do row operations. Let's use our calculator, solve the system of the calculator, but we are going to use the RREF of matrix A in our calculator. And you'll see in a moment why I wanted to make sure it wasn't just to practice your calculator keystrokes, right? I want to go and I want to edit matrix A, but I want to edit it to this new matrix. Double check your entries. 74, 108, 34, 31, 46, 15, 121, 15, 22, 7. Quit. Just hit second entry. And bam. Oh. What's going on here? Look at my last row. Well, this is a dagger. Right? So notice what happened here. So let's go, when you're doing your homework, even if I always want you to write down the reduced row echelon form. But I didn't end up, right? This was a 2 and this was a 5. Then I had 1, 1, -1. And then what was wrong with the last row? Oof. Right? This is basically saying that 0 equals 0. Well, isn't this a true statement? 0x plus 0y plus 0z, isn't that equal to 0? Isn't this true, and isn't it always true? Do you remember from Algebra 1 and from AAF what we said about a system when we solved it and we got a statement that is always true? Right? In Algebra 1, this was coinciding lines. Here, for us with planes, it means I've got one of those. I do have an intersection of 3 planes, but they intersect in a line. So, how we handle this is first, given this statement, This is a consistent system. I do get an answer. I just get lots of answers, and it's dependent. Let me ask you again to reach back into your Algebra 1 brain and also AAF. When we were doing these, if you have an coinciding lines, what did your answer look like? You didn't just write 0 equals 0, did you? No, you wrote the equation of the line. So here, if the solution is a line, you have to find the equation of that line, and I want it to be in parametric or vector form. So how do we do that? Well, what this statement means, since 0 is equal to 0, it means that z is free. It's free, woohoo! What that means is z can be anything. I mean, so can anybody else, but with all of these zeroed out, let's make z equal to the parameter t. Ooh, sneaky! That's so sneaky. Now go and write what this represents. Remember, this is 0x plus 1y plus z, but what did I make z equal to? And then go up to the last one. This is 1x plus 0y plus 2z, but I made z because it's free. Do you remember what we did for this to write the parametric, right? Get x by itself up there. Which means that the vector, right, that's the parametric form. Vector form would be the 0.5, -1, and 0, plus the parameter t times, you see the warm up, right? -2, -1, and 1. Oh, snap. All right, so you'll have some like that on your homework. Last one. Put this into your calculator and write down what reduced row echelon form looks like. I'm not going to do this on my calculator. I'm going to trust you to do it. Right? 3, 1, 7, and 15. 2, 1, 4, and 11. Careful. -1, 0, -3, and -2. Your augmented matrix. And then when you do your ring of fire, you get 1, 0, 3, 0, 0, 1, -2, and 0, and I get 0, 0, 0, 1. And this is why it's important that you can read and understand what this is saying to you. This statement says 0x plus 0y plus 0z, which is equal to 0, is equal to 1. What kind of statement is that? Why, it's a lie, Ms. Getz. That's never true. Since this is always false, what do you think your math is telling you? This system is inconsistent. Okay? So, lesson learned. If you end up with your identity down here, right, if you do end up with the identity for your 3 by 3 matrix, you just can read your solution and you have an independent solution and you read it from your answer column. If you end up with the last row zeroed out, that means that you've got a consistent system and you've got an extra step that you need to go through. You need to write the equation of the line. If you end up with all zeros and a 1, that means you have the easiest of work at, and you just write there is no solution, which means you have an inconsistent system. All right? So again, you are not going to be responsible to come up with the row operations on your own this year. That is for your higher level and linear algebra class. You will not be doing any of this kind of any matrix work at all in calculus next year. So keep your notes. Be organized. Okay. Bye for now.